Welcome to this coding walkthrough. Today, we'll be solving LeetCode problem number 1523, count odd numbers in an interval range. This problem is a great exercise for practicing mathematical reasoning and efficient counting techniques. Let's dive in and explore the solution step by step. The problem asks us to find the total count of odd numbers within a specified range, inclusive of the bounds. For example, if the range is from 3 to 7, the odd numbers in this range are 3, 5, and 7. Since there are 3 odd numbers, the output is 3. Another example is when the range is from 8 to 10. In this case, the only odd number is 9, so the output is 1. The task is to write an efficient solution to determine this count for any given range. Now, consider the case where the range is just a single number, such as 11 to 11. Since the range contains only the number 11, and 11 is odd, the output is 1. On the other hand, if the range contains a single even number, like 4 to 4, the result will be 0 because the range does not include any odd numbers. This highlights that the solution needs to handle both single number ranges and standard ranges. Additionally, we need to account for edge cases. For instance, ranges where all numbers are even, like 4 to 6, will result in an odd count of 0. Conversely, ranges with all odd numbers, such as 3 to 5, would result in the count being equal to the total numbers within the range. Finally, for very large ranges, such as 1 to 10 to the power of 9, the solution must be efficient and avoid iterating through each individual number, which would be computationally expensive. To solve this problem efficiently, we can use a mathematical approach. First, observe that the total count of odd numbers from 1 to any number x can be calculated as x plus 1, divided by 2, rounded down. Using this, the count of odd numbers in the range from low to high is simply the difference between the odd counts from 1 to high and from 1 to low 1. This formula, expressed as high plus 1 / 2 minus low / 2, allows us to compute the result directly without iterating through the range. By leveraging this formula, we ensure the solution is fast and works well even for very large ranges. To solve the problem of counting odd numbers in an interval range, we can start by exploring a simple brute force approach. The idea here is to iterate through each number in the range from low to high and count the ones that are odd. We initialize a counter to 0, then loop through all the integers in the range. For each number, we check if it is odd using the modulo operator, x%2 is not equal to 0, and if it is, we increment the counter. Finally, we return the value of the counter. While this method is easy to understand and implement, it has a major drawback. Its time complexity is O(n), where n is the size of the range, which can be very large. For instance, if high-low is close to 10 to the power of 9, this approach would be far too slow to execute efficiently. The brute force approach, though straightforward, becomes impractical for large ranges due to its inefficiency. To address this, we turn to an optimized approach that leverages a mathematical observation about odd numbers. Odd numbers follow a predictable pattern, they alternate with even numbers, so we don't need to iterate through each number in the range. Instead, we can calculate the count of odd numbers directly. Here's the key insight: the count of odd numbers from 1 to any number x is given by the formula x plus 1 / 2. Using this, we can determine the count of odd numbers in the range low, high, by subtracting the count of odd numbers up to low 1 from the count of odd numbers up to high. This gives us the formula high plus 1 / 2, low / 2. By relying on this arithmetic observation, we eliminate the need for iteration entirely. To implement this optimized approach, we follow just a few steps. First, compute the count of odd numbers up to high using the formula high plus 1 / 2. Next, compute the count of odd numbers up to low 1 using the formula low / 2. Finally, subtract the second result from the first to get the total number of odd numbers in the range low, high. This method is extremely efficient, with a time complexity of O(1), since we only perform a few arithmetic operations, and a space complexity of O(1), as no additional memory is required. The advantages of this approach are clear: it is computationally efficient, avoids unnecessary iterations, and works seamlessly even for the largest valid input ranges. These benefits make it the ideal strategy for this problem. The mathematical approach is the chosen solution for this problem because it is both efficient and elegant. Unlike the brute force method, which is too slow for large ranges, this optimized formula computes the result in constant time, regardless of the range size. However, this approach does have a trade-off. It is highly specific to problems where such patterns, like the alternation of odd and even numbers, exist. For scenarios without such predictable patterns, this method would not be applicable. The key insight here, the aha moment, was realizing that odd numbers follow a predictable sequence and leveraging this pattern to derive a simple arithmetic formula. The final solution, shown in Python, is exceptionally concise and captures the essence of the optimized approach. By directly calculating the count of odd numbers using the formula high plus 1, ///2, low // 2, we arrive at the result without any loops, making it both clean and efficient. To solve this problem, our goal is to count all the odd numbers within an inclusive range defined by two integers, low and high. As a quick reminder, odd numbers are integers that are not divisible by 2, such as 1, 3, 5, and so on. For instance, if the range is 3, 7, the numbers included are 3, 4, 5, 6, 7. Similarly, 4, 4, 10, the numbers are 4, 5, 6, 7, 8, 9, 10. Now, instead of iterating through every number in this range to check if it's odd, we can use a more efficient approach by leveraging the mathematical properties of odd numbers. One important insight is that odd numbers alternate with even numbers. This means the total count of odd numbers in any range can be directly calculated based on whether the endpoints, low and high, are odd or even. For example, if both low and high are odd, we include both endpoints in our count. If one endpoint is odd and the other is even, we adjust the count accordingly. And if both are even, the odd numbers will lie strictly between low and high. To make this approach more concrete, we can use a formula to calculate the total number of odd numbers up to any integer x. The formula is x plus 1, // 2. This works because odd numbers occur at regular intervals, specifically every other integer. For instance, for x equals 7, the odd numbers are 1, 3, 5, 7, which gives us a count of 4. Plugging into the formula, 7 plus 1, // 2 equals 4. Similarly, for x equals 6, the odd numbers are 1, 3, 5, which gives a count of 3, and 6 plus 1, // 2 also equals 3. With this formula, we can now calculate the count of odd numbers in any range, low, high, using the difference of counts, high plus 1, // 2, low // 2. This works because high plus 1, // 2 gives us the total count of odd numbers up to high, while low // 2 excludes the count of odd numbers below low. To execute the algorithm, we simply compute both of these values, subtract them, and return the result. This approach provides several key advantages. By relying on the formula high plus 1, // 2, low // 2, we avoid the need to iterate through the range. This optimization reduces the time complexity to 1, as it involves only a few arithmetic operations. Additionally, the formula is robust and handles all edge cases. For example, it works for small ranges, such as when the range includes only one or two numbers. It also correctly accounts for situations where both low and high are odd, both are even, or one is odd and the other is even. Furthermore, this algorithm does not require any extra data structures, as it operates directly on the input values. In terms of space complexity, this means we achieve 1 as well. To summarize, the combination of mathematical optimization, constant time complexity, and minimal space usage makes this approach highly efficient. Let's walk through a couple of examples to see how this works in practice. In the first example, suppose low equals 3 and high equals 7. First, we calculate high plus 1, // 2, which is 7 plus 1, // 2 equals 4. This represents the count of odd numbers up to 7, which are 1, 3, 5, 7. Next, we calculate low // 2, which is 3 // 2 equals 1. This represents the count of odd numbers below 3, which is 1. Subtracting these results, 4, 1 equals 3, tells us there are 3 odd numbers in the range, 3, 7. For the second example, let's take low equals 8 and high equals 10. We compute high plus 1 / 2, which is 10 plus 1 / 2 equals 5, corresponding to the odd numbers up to 10, 1, 3, 5, 7, 9. Then, low / 2 is equal to 8 / 2 equals 4, representing the odd numbers below 8, 1, 3, 5, 7. Subtracting these, 5, 4 equals 1, gives a count of one odd number in the range 8, 10. These examples demonstrate the formula's accuracy and efficiency. The problem asks us to count all odd numbers in the inclusive range, low, high. Instead of iterating through all numbers in the range, which could be inefficient for large ranges, we use a mathematical approach to directly compute the count of odd numbers. Step-by-step explanation. 1. Counting odd numbers up to high asterisk. Every second number is odd, so the count of odd numbers from 1 to high can be calculated as high plus 1 / 2. For example, if high equals 7, the odd numbers are 1, 3, 5, 7, and the count is 7 plus 1 / 2 equals 4. 2. Counting odd numbers up to low 1 asterisk. Similarly, the count of odd numbers from 1 to low 1 is low / 2. For example, if low equals 4, the numbers up to low 1 are 1, 3, and the count is 4 / 2 equals 2. 3. Subtracting the counts asterisk. To find the count of odd numbers in the range, low, high, we subtract the count of odd numbers up to low 1 from the count of odd numbers up to high. Using the earlier examples, if low equals 4 and high equals 7, the count of odd numbers in the range, 4, 7, is 4, 2 equals 2, odd numbers are 5, 7. Complexity. Time complexity asterisk. The solution runs in constant time O1, as it involves only basic arithmetic calculations. Space complexity asterisk. The solution uses O1 space, as no extra data structures are used. This efficient mathematical approach ensures that the solution works even for very large ranges without iterating through each number. This is the Java implementation of LeetCode problem number 1523. Count odd numbers in an interval range. The logic mirrors the Python implementation, with type declarations and Java-specific syntax. The solution calculates the number of odd numbers in the range, low, high, using integer division, ensuring a concise and efficient approach. The class structure is complete, and the method countOdds provides the required functionality. To solve this problem, we aim to count the odd numbers within a specific interval, low, high, in an efficient manner. Instead of iterating through each number in the range and checking if it is odd, we leverage a mathematical formula to calculate the result directly. Let's start with an example where low equals 3 and high equals 7. First, we count all the odd numbers from 1 up to high. The formula for this is high plus 1 / 2, which gives the count of odd numbers up to a given number. Substituting high equals 7, we calculate 7 plus 1 / 2, resulting in 4. So, there are 4 odd numbers up to 7, 1, 3, 5, 7. Next, we count the odd numbers up to low 1. Here, the formula is simply low / 2. Subtracting 1 from low equals 3, we calculate 3 to 1 / 2, which results in 1. This means there is just one odd number up to 2, 1. Now, to find the odd numbers specifically within the range, low, high, we subtract the count of odd numbers up to low 1 from the count of odd numbers up to high. Using our earlier results, this means subtracting 1 from 4, giving 3. Therefore, there are 3 odd numbers in the range, 3, 7, 3, 5, 7. Let's look at another example where low equals 8 and high equals 10. Again, we first count the odd numbers up to high using the formula, high plus 1 / 2. Substituting high equals 10, we calculate 10 plus 1 / 2, which equals 5. This means there are 5 odd numbers up to 10, 1, 3, 5, 7, 9. Then, we count the odd numbers up to low 1, which is low 1 / 2. Subtracting 1 from low equals 8, we calculate 8 to 1 / 2, giving 3. This tells us there are 3 odd numbers up to 7, 1, 3, 5. To determine the count of odd numbers within the range, low, high, we subtract the count of odd numbers up to low 1 from the count of odd numbers up to high. From our calculations, we subtract 3 from 5, resulting in 2. Thus, there are 2 odd numbers in the range 8, 10, 9. Finally, let's consider a smaller range where low equals 1 and high equals 1. Using the same approach, we count the odd numbers up to high. The formula high plus 1 / 2 gives 1 plus 1 / 2, which equals 1. This means there is one odd number up to 1, 1. Similarly, we count the odd numbers up to low 1. Subtracting 1 from low equals 1, we calculate 1 to 1 / 2, which equals 0. This indicates there are no odd numbers up to 0. Finally, to find the count of odd numbers within the range low, high, we subtract the count of odd numbers up to low 1 from the count of odd numbers up to high. Using our results, 1, 0 equals 1, meaning there is one odd number in the range 1, 1, 1. To summarize, this approach is highly efficient because it avoids iterating through the range entirely. Instead, it calculates the result directly using simple mathematical formulas. It handles edge cases, such as when the range includes only one number or when the range contains no odd numbers, seamlessly. The core idea is based on the formula n plus 1 / 2, which calculates the count of odd numbers from 1 to n. By subtracting low / 2, we remove any odd numbers that fall outside the given range, ensuring an accurate count. The time complexity of the solution is O(1), which means it runs in constant time regardless of the size of the input range. This is because the algorithm performs a fixed number of arithmetic operations. Specifically, calculating count_high involves adding 1 to high and performing integer division, both of which are constant time operations. Similarly, calculating count_low is just an integer division, and subtracting count_low from count_high is a single subtraction operation. Since none of these operations depend on the size of the input range, the overall time complexity remains O(1). Now, looking at the space complexity, this solution is also O(1), because it doesn't use any data structures that scale with input size. The algorithm only uses 2 integer variables, count_high and count_low, which require constant memory. As no additional memory is allocated, the space usage stays fixed no matter the size of low and high. Therefore, both time and space complexities for this solution are O(1). Let's compare this with a naive or brute force approach. In the naive method, we iterate through each number in the range low, high, and check if it is odd using the modulo operation. The code might look something like this: we initialize a counter, loop through all numbers in the range, and increment the counter for each odd number. While this approach may seem straightforward, its time complexity is O(n), where n is the size of the range, calculated as high, low plus 1. This is because we perform an iteration for every number in the range, and the modulo operation to check if a number is odd is O(1). As a result, the overall time complexity of the naive approach becomes O(n). In terms of space complexity, the naive approach still has O(1) complexity because it only uses a single counter variable to store the result. However, the optimized solution provides significant advantages. By leveraging arithmetic calculations instead of iteration, the optimized solution avoids looping entirely, allowing it to calculate the count of odd numbers in constant time. This makes the optimized approach scale independently of the size of the range low, high. Additionally, when analyzing the solution for best, average, and worst-case scenarios, the time and space complexities remain constant. This is because the algorithm performs a fixed number of operations regardless of the input values. There's no iteration, no recursion, and no dependency on the size of the input, which means the complexity stays O(1) in all cases. In conclusion, the optimized solution is far more efficient than the naive approach because it achieves constant time and space complexity through the use of mathematical properties of odd and even numbers. By eliminating the need for iteration, the algorithm ensures that the number of operations remains fixed, making it highly scalable and efficient for any input range. This makes the solution not only optimal but also robust for a wide variety of use cases. When tackling this problem, there are a few common mistakes you should be aware of to avoid errors in your solution. First, remember that the range low, high is inclusive. This means both low and high are part of the range, so it's easy to miss counting low, especially if it's odd. Next, Brute forcing through every number in the range becomes a problem when the range is very large. Think in terms of millions or even billions. This can cause your solution to exceed the time limits. Another potential pitfall is mishandling edge cases. For instance, if low equals high, or if both low and high are either even or odd, it's critical to ensure your logic works correctly in these scenarios. Additionally, small mistakes in mathematical calculations, like forgetting to add 1 when low is odd, can result in undercounting the odd numbers. Finally, avoid hardcoding specific conditions for every possible combination of low and high being odd or even. This makes the code unnecessarily complex and prone to errors. This problem is often used in interviews to evaluate several key skills. First, it tests your ability to recognize patterns in numbers, such as how odd and even numbers alternate and how this can be leveraged for efficient counting. Efficiency is another critical aspect. While brute force might work for small ranges, interviewers are looking for you to optimize your solution, ideally using a simple mathematical formula. Handling edge cases is also important. For instance, scenarios like low equals high or very large ranges require careful consideration, and clarifying these during the interview demonstrates your thoroughness. Finally, being able to explain the trade-offs between approaches is essential. For example, you might highlight why an O(1) mathematical formula is far superior to an O(n) iterative solution. This ability to analyze and articulate the reasoning behind your choices is highly valued by interviewers. This problem is conceptually similar to several others on LeetCode, which can help you build a stronger understanding of related techniques. For example, problem number 1491, average salary excluding the minimum and maximum salary, also emphasizes careful handling of boundary values in edge cases. Another related problem is number 1295, find numbers with even number of digits, which involves similar counting logic applied to a different condition. Problem number 204, count primes, introduces efficient counting within a range, which aligns with the need for optimization in this problem. Lastly, problem number 2315, count words obtained after adding a letter, is another counting problem that involves meeting specific conditions. Exploring these problems can deepen your problem-solving skills and reinforce the concepts you've learned here. There are multiple approaches to solving this problem, each with its own trade-offs. The most intuitive method is brute force iteration, where you loop through every number in the range, low, high, check if it's odd, and count it. While this is straightforward, the time complexity is O(n), making it impractical for large ranges. A much more efficient approach is the mathematical formula, high plus 1, //2, low //2, which directly calculates the count of odd numbers in constant time, O(1). This is the optimal solution for large ranges, but it does require a solid understanding of the formula and careful handling of edge cases. Another alternative is to simulate the counting process with a step size of 2, starting from the first odd number in the range. This is faster than brute force but still has an O(n) time complexity in the worst case. While it's an improvement, it doesn't match the efficiency of the mathematical approach. Choosing the right method depends on the constraints and the context in which you're solving the problem. Great job following through this problem. To recap, we used a mathematical approach to efficiently count odd numbers in the given range without iterating. This solution highlights the importance of modular arithmetic and thinking about edge cases carefully. Thank you for watching, and don't forget to like and share if this helped you. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!